Hi, good morning or good afternoon, everyone, whenever you're watching this. Today I'll be presenting our work on heat treatment and hardness testing. I've made a presentation that'll walk you through the fundamentals of heat treatment processes, the importance of hardness testing, the methodology I used, key results, and finally some takeaways from the experiment. By the end, you should be able to see how altering microstructure impacts material performance in real world applications. All right, let me pull up the PowerPoint. Mm, okay. All right, let's start with the objectives. I aim to understand the fundamentals of heat treatment, which involves heating and cooling metals in a controlled way to change properties. Properties like hardness, strength, and ductility without changing the overall shape. I also wanted to highlight the significances of hardness testing, different hardness tests like the Rockwell B for softer materials, Rockwell C for harder steels, BC for intermediate ranges, and Burnell for coarse structures. Um, so these all help determine how resistant a material is to deformation and wear. Another goal was comparing experimental versus theoretical values to see how close our actual results match with the expected properties. So uh, any deviations could indicate process variation, material inconsistency, or just simple measurement error. Finally, I wanted to connect this to real-world applications such as gears in automotive systems, turbine blades in aerospace, and precision cutting tools in manufacturing. Um, I'll quickly go over the methodology. Um, for the methodology, I prepared samples and subjected them to or I was given samples that were prepared and subjected to different heat and treatment processes. I then measured the hardness using various scales, which were the Rockwell B, Rockwell C, Rockwell BC, and then Bernal on each sample. My aim was to capture how each heat treatment method altered the hardness profile and then compare the results across different measurement systems. Um, each test type uses different indenters, forces, and scales, so cross comparison really gives a fuller picture of material performance after treatment. So now let's take a look at the graphs. So here we see the Rockwell B hardness results. The key observation is the values stayed relatively consistent across samples, suggesting a uniform material response to the applied heat treatment under HRB conditions. This scale is more sensitive to softer metals, so while differences may not be dramatic here, it still provides useful confirmation of material stability. Um, Here we have the Rockwell C results. So in contrast, the Rockwell C results show more pronounced changes. Some samples recorded marked increases in hardness after treatment, indicating that the heat treatment successfully increased resistance to indentation for harder steels. This scale is particularly useful for tool steels and components that require wear resistance in high stress environments. So like probably like gears and stuff, maybe. And then this is the Rockwell BC results. The BC results serve as an intermediate measure between the B and C scales. So they basically bridge the gap, confirming that for certain materials, heat treatment effects sit in like a middle hardness range. Um, this helps when dealing with alloys that don't fall cleanly into the soft or hard category, but still need predictable hardness values. So there's that. And then finally, we have the Brinell results. This method uses a larger ball indenter, so it's well suited for coarse grain materials. Our BHN data aligns closely with the Rockwell trends, reinforcing the idea that hardness changes were consistent across different testing methods. So this cross validation actually gives me more confidence that uh, my findings were pretty reliable. I'll come into the most important part, the takeaways. From this experiment, the main takeaways I would say are first one is heat treatment, of course, can significantly alter hardness, but the degree depends on the metal and the specific process used. Um, Second is different hardness tests target different ranges. So using multiple methods give give like a more complete view of material performance. Um, and then third, consistency across testing methods is a good indicator that your experimental process was sound. So yeah, you want to try a bunch of stuff to make sure that you have consistency. Um, Lastly, I will start concluding here. Um, Heat treatment and hardness testing are essential tools in engineering different types of materials, but in understanding how to control microstructures is what makes it really important. We can tailor materials for applications where performance, safety, and cost efficiency are critical. Um, the data from our test not only confirmed theoretical expectations, but also demonstrated the value of cross-method validation and hardness measurement. So again, like I said, you want if you want consistency, you want to use all the three methods that were used in this lab, and then that's going to give you a broader range uh of validation to make sure that you actually have the right data. So yeah, thank you for listening. I think that's about it.